and we start rolling. Or in the words of a generation ago, we start rolling, 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 rolling. What? Keep rolling, 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 rolling. Sorry about that. I'm kind of embarrassed to admit that I actually know Limp Bizkit. Right. So here we are. Everybody should be able to see the slides. We'll talk a little bit about systematics. If that's not a word that you know, systematics is basically the principles and theories behind biological classification. You know, why do we classify living things the way that we do? What are the principles that lie behind all of that kingdom, phylum, class, order, family, genus, species business that you've all learned about? And then, of course, what does this have to do with the ultimate origin of eukaryotes, including animals? And as many things do, it goes back to there. It goes back to my home slice Charles Darwin, or as I like to call him, Chuck D, who realized that if this whole evolution business were actually true, it would force you to classify organisms in a different way. It would give classification a new basis. And as he said in Origin of Species, back in 1859, our classifications will come to be, as far as they can be so made, genealogies. We possess no pedigrees or armorial bearings. That means British coats of arms and things like that. And we have to discover and trace the many diverging lines of descent in our natural genealogies by characters of any kind which have long been inherited. So you could work out what organisms were related to what organisms and how closely they were related by looking at stable characters that had been inherited for a long time. Maybe not the minor characters of things like beak shape and feather color that Darwin had looked at when he had studied domestic pigeons. If you don't know, Darwin got a lot of his ideas about how natural selection might work from studying fancy pigeons. He was quite a pigeon fancier for a while. So maybe not those superficial things that had been created by selection just over the course of a few years, but features that have been around for a long time might be the ones that you could use to work out how different species of life were related to each other and how distantly they might be related. And that's a famous diagram from one of his very early notebooks. This is from back in 1837. This is 21 years before he actually published his evolutionary theories, but he was thinking about it at this stage. And it shows how old species, represented by that number 1 down at the base, might branch into new species, which he's labeled here A, B, C, and D, plus a number of extinct species that don't point to any one of those letters. So species branch, they divide into new species, and this is a very long process that's been going on for as long as there's been life. And yeah, one of his more famous quotes compares the history of life to a branching tree. The affinities of all the beings of the same class have sometimes been represented by a great tree. I believe this simile largely speaks the truth. As buds give rise by growth to fresh buds, and these, if vigorous, branch out and overtop on all sides many a feebler branch, so by generation I believe it has been with the great tree of life, which fills with its dead and broken branches the crust of the earth, what he means is fossils, and covers the surface with its ever-branching and beautiful ramifications. Rather, one of the few places in his work where he actually gets kind of poetic. And you've probably seen diagrams like these. These were drawn up by a German guy by the name of Ernst Haeckel, who was also a very important invertebrate zoologist. And he drew up these rather, quasi-realistic diagrams of evolution as a tree. You may not be able to see all of the detail, but he starts at the base of the tree with moneren and amöben, bacteria and amoebas. So the bacteria and the protists are down at the bottom. A bit up there, he's got the Würmer, that's the worms, and the Pflanzentiere, that's things like corals and stuff like that. Gliedertiere, the arthropoda, the insects, which is what 3/4 of all animal species, is a little side branch over on the left about midway up. And he goes up through the Shadowlosa, the jawless fish, and Urfische, that's sharks, and amphibian. And up there at the top, he's got all of the mammals with the Walfische, the whales, and the Raubtiere, the carnivores, and the Affen, the apes. And up there at the very top of the whole tree, mention humans. So it's a tree, but kind of with one single stem, leading up from the goo through the zoo to you, as we say, from the amoebas and bacteria through various animal life, with humanity up there at the tippy top. Okay, you can definitely critique that particular view of life, but another question is, how does he know where to put the branches? How can you tell what branches off from what? And we'll skip over a ridiculous amount of details all the way up to the 1950s, when there's a German entomologist named Willy Hennig. And Hennig has developed a method for trying to reconstruct this tree of life in a rigorous way. It's very easy, if you're doing classifying, to group things together on the basis of you kind of think they look alike, or you think they've got some things in common, but maybe you're not too articulate about what those might be. Hennig's method is an attempt to try to take the subjectivity out of it and say, I hypothesize that these two species share a common ancestor because they share this, this, and this. It's not a perfect method, and it's not guaranteed to be right, but it forces you to lay your cards on the table and say, okay, this is why I think that species 1 and species 2 are more closely related to each other than either one is to any others. And it's a method you've probably been exposed before, probably in Biology 1441, and it's called cladistics. Cladistics. All right, eyes are getting a little bad there. Cladistics. Klados happens to be Greek for a branch, if you're wondering where the word comes from. By the way, I am never going to require that you learn Latin and Greek roots. I'll never ask you what's the ancient Greek root word for branch, but I do break down a lot of the vocabulary that I give. Sometimes that's useful. Sometimes that helps people remember. Sometimes you encounter other words derived from these roots in other classes, or possibly even professionally. Some of you folks might end up having to learn medical terminology or things like that if you go on to medical school, for example. So I'll never test you on it as such, but I'll give it to you as a way of trying to help you retain the material and learn some things that, if you retain, might stand you in good stead in classes further down the line. So klados is Greek for branch. So cladistics means branchistics. And it breaks down to this. Evolutionary changes, Hennig says, are relatively rare. They do happen, but normally if you breed, two dogs together, you get a litter of puppies that look very much like their parents. You're not likely to see any novel traits. They do sometimes happen, and if that, of course, is what animal breeders use. But organism phenotypes do not get completely redone in every generation. You're not going to get 3 generations of breeding elephants and you're getting giraffes, right? You're not going to have 3 generations of crocodiles and boom, all of a sudden you get a crocoduck. Evolutionary changes are relatively rare. Most of the time, heredity gets everything right. And it's even more rare that you get convergent evolution, which is the independent gain of the same or similar traits or features in lineages that are unrelated to each other. It does happen. One of the most famous examples Darwin realized when he visited Australia as a young man and discovered that Australia's got things like marsupials that look exactly like moles, these burrowing mammals, marsupials that look a lot like flying squirrels, marsupials that look a lot like anteaters and yet aren't. They belong to a completely different branch of the mammalia, the marsupials, not the placental mammals. And so there was a huge amount of convergent evolution there, and Darwin actually said that it was almost as if there'd been 2 different creators at work. One God that made life everywhere else in the world, and one that made Australia. So convergent evolution does happen, but it's even more rare. Most of the time, organisms that are not closely related to each other are going to evolve on independent trajectories. And it won't be that often that they end up evolving towards the same phenotype. And so if you have 2 or more taxa, remember, a taxon can be a species or it can be a larger grouping. It's any biological group. If 2 or more taxa share a trait, the simplest explanation is that they inherited it from a common ancestor. It's not the only possible explanation. It could be convergence. It could be due to chance. It could be because evolution is having a weird sense of humor or something like that. But the simplest explanation is that if 2 or more taxa share a trait, it's because they inherited it from a common ancestor, because convergence is rare. And the more traits are shared between 2 or more taxa, the more likely it is that these taxa inherited it from a common ancestor. So here's a great example of convergent evolution. On the left, you've got a flying squirrel, similar to ones you could find around here. The neighborhood where we used to live in Conway actually had them. I used to had one glide past my nose as I was walking to school one day. On the right, that's a sugar glider. That's an Australian mammal. And you can see that they've both got this gliding membrane. They've both got it's called a patagium, this squarish, furry membrane from wrist to ankles that enables them to glide. But if you look at the totality of the anatomy, not just the patagium, each one shares far more features with other animals than they do with each other. Flying squirrels are rodents. They've got tooth gaps and incisors that grow throughout life, so they have to keep gnawing them down. They reproduce with placental reproduction. Babies grow in the uterus, nourished by a placenta. Sugar gliders are marsupials. They give birth to very underdeveloped offspring that mature in a pouch. They've got marsupial features like marsupial-type teeth and nasal bones and epipubic bones on the pelvis and things like that. So the totality of features groups flying squirrels with other rodents and sugar gliders with other marsupials, and the patagium is almost certainly a case of convergent evolution. And yeah, I've just kind of violated one of my rules by using mammals as an example in an invertebrate zoology course, but there you are. We've got to start somewhere. So here's the thing. If you take any set of living things, any set of taxa, they're related to each other by common ancestry somehow, unless life evolved twice on Earth, and it almost certainly didn't. There's simply too much very deep biochemical similarities that all life shares. So we'll assume what's probably right is that life only evolved once. And that means any group of taxa that you pick goes back to a common ancestor if you trace it back far enough. You know, you share a common ancestor with an oak tree if we could trace your family tree back far enough. Obviously, you did not evolve from oak trees, nor did they evolve from you, but the two of you would go back to some common ancestor. We probably don't really know what it was, and it would have lived a few billion years ago, but it's a logical necessity that you do if life only appeared once on Earth. So any set of taxa, I could pick you and a wombat and a mushroom and a slime mold and a banana tree, and all five would go back to a common ancestor if we could take it back far enough. Now, for any set of n taxa, the total number of trees that you could draw is 2n minus 3 double factorial. Okay, that double exclamation point does not mean that I'm really excited about 2n minus 3. A single exclamation point is a factorial, and n factorial is n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, ... back to 1. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Double factorial, you multiply by every other number. So 10 double factorial would be 10 times 8 times 6 times 4 times 2. If we have 5 taxa, the total number of trees that we could draw to show how they're related is 7 double factorial, right? It's 2n, 5 times 2 is 10, minus 3 is 7. 7 double factorial is 7 times 5 times 3 times 1, which I can't calculate because I haven't had my coffee, but you can figure it out. That's the total number of possible trees. If you're studying 10 taxa, there are 34 million possible trees that you could draw up. If I took, I don't know, you, a shrimp, a monkey, a wombat, an aardvark, a kangaroo, a slime mold, an oak tree, a daisy, and E. coli, okay, that's 10 taxa. There are 34 million possible ways in which we could all be related through common ancestry. How do you pick the best out of those 34 million? Well, the best is not guaranteed to be the right one, but the one that fits the data best, the one that you prefer under cladistics rules. The preferable one is the one that maximizes the number of characters that are shared and minimize the number of convergences. So of those 10 taxa that I wrote, you and the monkey share a lot of features in common. You've got forward-facing eyes, large-sized brain, tendency to put your vertebral column underneath your spine and adopt what's called vertical climbing and leaping posture, opposable thumbs, thumbs that you can touch to your other fingers, fingernails instead of claws or talons or hooves or anything like that. There's a lot of characters that you share in common. And a tree that put you and a monkey as each other's closest relatives, descended from a most recent common ancestor, is not guaranteed to be right, but it's likelier to be correct than one that put you and a slime mold as each other's closest relatives and put the monkey related to the banana tree. Okay, the monkey might like being on the banana tree, but the monkey is not closely related to the banana tree. So we look for the tree that maximizes the number of characters that are shared. That's called synapomorphies. And we look for the tree that minimizes the number of instances of convergent evolution that you have to assume. There'll always be some, but you look for the tree that minimizes convergences and character state reversals, and we call those homoplasies. And that's called the principle of parsimony. Parsimony means being stingy, being careful with your money. All right, if you don't spend your money on anything other than absolute necessities, you would be parsimonious. And in this case, it means don't invoke convergent evolution. Don't spend your instances of convergence when you don't have to. Don't invoke convergence unless there's no better explanation. Pick the explanation for how your organisms got here that's the simplest. It's not guaranteed to be right, but it's the one you should go with if you have to choose between, 34 million possible trees. Don't pile up convergences if you don't have to. Okay, I promise I'm going to get to some pictures soon. I'm assuming everybody can hear me and that I'm speaking clearly. If I'm not, let me know in chat. Let me know if there's ways I can improve this. This is not as good as an in-person course, but I do want to make it suck as little as possible. Okay, so let's say you've got a family tree drawn up. You can start dividing the species on it into groups, and a group that includes a common ancestor and all of its descendants is said to be monophyletic. Give you a human example. Round about 1620, I think, maybe 1619. No, a little later, I think 1630. So about 10 years after the Pilgrims came, there was a ship of colonists that came from England and settled in what's now the state of Connecticut, settled in a town that's now called Clinton, although back in the day it was called Killingworth. One of them was a guy named William Kelsey. And William Kelsey married, and he had kids, and those kids had kids, and those kids had kids. And after something like between 10 and 15 generations, there are hundreds of thousands of people, including me, who are descended from William Kelsey. My father's mother was a direct descendant. She was Esther Kelsey. And there's an entire book called Kelsey Kindred. Actually, it's 4 volumes that I've got at home. And what that book contains, or at least, as of about the 1970s when it came out, is William Kelsey and everybody who is descended from him that could possibly be traced. That's a monophyletic group. It's everyone that's descended from a single common ancestor, this one person who we could document did live and have kids. So that would be a human example of a monophyletic group. It's not as simple in human biology because humans don't have the kind of inheritance we're talking about, in that, you know, our family trees form webs and networks instead of single branching trees, right? I've got other ancestors other than William Kelsey. In fact, I've got quite a lot of them, and so do you. Certainly my mother comes from a whole different set of ancestors, and, you know, I'm blended from all of them, and so is every one of you. But this may still help you to visualize what I mean by a monophyletic group. When I had to go to my grandmother's funeral, just about everybody down in that church basement in Iowa was directly descended from her. There were a lot of us that went back to this common human ancestor. And you can do something analogous in biological classification. I'm going to pause this for just a second because somebody has just joined, and Savannah has just joined. Good morning, Autumn. Good morning, Savannah.
Hi.
Hi.
My Wi-Fi's been on and off, and I did not get your email with the code until about a couple minutes ago.
Okay. All right. I'm sorry about that. I'm not upset or anything like that. Once we're done, it'll be this afternoon, but I'll get these uploaded to YouTube, and you'll be able to come back and pick up on what you missed.
Awesome. Perfect. Thank you.
Okay. Groovy. Good morning, Savannah. Or is that Savannah I was just talking to?
That was me.
Okay. Good morning to both of you. There. I will go ahead and resume the presentation. If you have a biological group that includes a common ancestor and some of its descendants, but not all, we'd call that paraphyletic. And a group that isn't based on common ancestry at all is polyphyletic. Most people who do systematics, you know, the study of the principles behind biological classification, try to include only monophyletic taxa. Paraphyletic ones are not considered valid. You have to start somewhere, and this is a way you can define groups rigorously if you've got a cladogram for them. An example of a polyphyletic group would be people used to group whales with fish. Now, that's based on convergence. Whales do superficially look like fish, right? They've got fins, and they're kind of torpedo-shaped, and they swim. But in everything else, they're mammals, right? They give milk. They give birth to live babies. They've got mammal-style features of the skeleton and soft tissue like diaphragms and things like that, lungs, no gills, no scales, ... So if we grouped whales and fish together in a grouping, that would be like Carl Linnaeus used to do back in the day. That would be a polyphyletic group. And I'll give you an example from the arthropods. This actually has something to do with the course. A traditional way of classifying arthropods was that insects, together with some relatives of theirs that don't have wings, like springtails and things like that, used to be classified in a big group called the hexapoda, shown in gray. Butterflies, beetles, and the other million or so species of insect would get put in that gray box. And crustaceans used to get placed in their own group. And that's everything from shrimp and crabs and lobsters to microscopic copepods and brine shrimp, aka sea monkeys, if you've ever heard of those, to parasitic groups like fish lice, and about 35,000 other species used to be placed in their own separate group. But according to some studies of DNA sequences, which I'll talk about later, and you're going to end up doing in one of these labs, it now looks as though this old class Crustacea is paraphyletic, meaning that the last common ancestor of all of those crustaceans, the last common ancestor of fish lice, copepods, brine shrimp, and crabs, was also an ancestor of the insects, of beetles, butterflies, and the other 900,000 so group in the insects. And so we can no longer talk about a biological class Crustacea, because every common ancestor of all of the Crustacea is also an ancestor of the insects. So defining Crustacea without including the insects would be a little bit like defining a family as everybody who's descended from William Kelsey, except for Uncle Wallace and his family, because we don't like them. Now, actually, I do like them. Uncle Wallace was a very nice man, but you see the point. If you're going to classify by common ancestry, you have to include all descendants of that common ancestor, because there's no objective way to decide who you're going to exclude. There's a piece of the actual cladogram that they drew up, and that's huge. You may not even be able to read all of the names on it, and you don't really have to. They can look confusing, but this is fundamentally based on representing the course of evolution by these branching trees and defining your groups on the tree based on, as best you can reconstruct it, common ancestry. I'm going to pause this for a second. How is everybody doing? I will assume that everybody's doing okay. All right. I tell you what, I'm going to go ahead and stop recording for now, and then I'm going to get up and make myself some coffee and take a few minutes to walk around, get my circulation back, make like Taylor Swift and shake it off, and I'll give you the opportunity to do the same. So we will pause this for right now. So I will, somewhere it's here. Oh no, that just turned off the camera.